we've covered the TDS equations, a set of two differential equations that describes the property relationships between six properties. I'd like to show you now how to use the TDS equations for quantifying changes in entropy for, let's say, a process 1 to 2, any process 1 to 2. And in this particular video, I want to talk about entropy, calculating entropy change of ideal gases. So those TDS equations are going to be extremely valuable to us for we're going to be able to derive an expression that says delta S, S2 minus S1 equals basically some, hate to use the word, some formula. Okay, so let's recap. What did we do so far? So far, we've got two differential equations. And so what we seek to do is find two expressions for delta S equals S2 minus S1 equals something. And then we'll be able to quantify. Well, let's review what do we already know about an ideal gas. So we're going to focus only on ideal gases. What certainly comes to our minds is the ideal gas equation of state. P times little v equals R times T, where remember R is R bar over the molecular weight. So R is the gas constant for a specific gas that you're working on. Another thing that you should know is the definition of the two specific heat values. C sub V is a derivative, du dt, and C sub P is another derivative, dH dt. So those are two definitions that you should know. Okay, so here we go. So now let's write down the two TDS equations, say from your textbook. I would, at this level, I don't have the nerve to say, you should memorize these. You should have these memorized. So I'm not going to say that. So I say, well, let's just write down the TDS equations that we've gotten from the textbook. And let's see, where do we go from here? Well, let's substitute, instead of du for an ideal gas, let's substitute CV dt, where CV can be some polynomial function. It doesn't have to be a constant number. It can be a variable function. Okay, let's substitute dH, Cp dt for dH. Okay, so we're trying to figure out, how do we find delta S equals? Hopefully you got it so far, right? Okay, so we started with this, and then we substitute du as Cv dt. Okay. Oh, let's see. I forgot a step. Divide both sides by t. So let's divide both sides by t first. Okay, so we've got ds is equal to Cv dt for du divided by t. All right, and ds, the second one, is Cp dt divided by t. And so I got a little thrown there because of my algebraic formulation. Okay, so we're going to divide by t, and we're also substituting du as Cv dt. All right. Now let's study the two right-hand terms in our two equations at the same time. Let's see. We've got P over T dV. Okay. And we've divided by T. So we've got V over T dP minus. Okay. So with me so far? Now let's do a little more studying. Let's look at the ideal gas equation of state and solve for P over T. P over T is R over V. And let's see, V over T is R over P. So now let's see okay, so now I'm down to this step. So I've made an ideal gas equation of state substitution. And let's study our differential equation. The left-hand side would be easy to integrate, wouldn't it? The integral of ds is just S. From state 1 to state 2, that's going to be our delta S, left-hand side. Okay, the next term, well, wow, I've got Cv divided by T dt. I've got the integral. CV might be some polynomial formula. I'm going to have to leave that alone. But let's look at these two right-hand terms, R over V dV. Do you see that R is a constant? So I've only got to integrate R over V dP. Okay. I said that wrong. R over V dV. Second equation minus integral R over P dP. And now these integrals become easy. This integral becomes easy, doesn't it? It's going to be a natural log. Natural log R natural log V2 minus R natural log V1. Well, that's going to be R natural log V2 over V1. And this term is going to be R natural log P2 over P1. Because we can integrate this pretty simple integral on the right-hand side. So let's see where we are so far. Okay, so I think I just went through that, didn't I? Okay, so the rightmost terms are easy to integrate, so I've written them down here. Okay, and so let's see, what have we got? Left-hand side, S2 minus S1, well, that's delta S, equals integral CV over T dt, still could be trouble, plus R natural log V2 over V1. Second TDS equation integrated, okay? Delta S is integral CP over T dt minus R natural log P2 over P1. Okay. Now the question is, what if CP is a variable? That could be. And what if CP is a constant number? One thing I want to remind you of, remember there's another fundamental about ideal gases that I didn't write down, and that is that Cp minus Cv always equals R for any ideal gas. So if Cp is a variable, then Cv is also a variable. But similarly, if Cp is a constant, then Cv is also a constant. That's going to be very powerful for us. And so what I want to do is step you through both situations. Okay, we've got an ideal gas. We're going to check that off. But now we're going to go to the situation one where Cp is a constant. And we'll look at the next situation where Cp is some variable. It could be a formula. Cp is some function of temperature. Okay, so here we go. When Cp and Cv are constant values, remember, if one of them is constant, the other one must be a constant. All right, so let's see. Here's our fundamental equation that we've derived. Now, if Cv is a constant, Cp is a constant, this integral becomes easy, doesn't it? The integral becomes, the first TDS equation becomes Cv natural log T2 over T1. And the second TDS equation becomes Cp natural log T2 over T1. So do you see with your eyes, this is an easy integral. It's 1 over T, the integral of 1 over T dt, because I've taken C sub P out of the integral when it is a constant. All right, so we've got something workable here. So look, this is calculator work. So if we have an ideal gas with constant specific heat, if we've got these temperatures and pressures, we can calculate, at stage 1 and 2, we can calculate delta S. So this is a very powerful relationship for ideal gases when Cp is a constant value. Therefore, Cv is also a constant value. All right, that's important, and we're going to include this in the recap. Now let's talk about dealing with variable specific heat ideal gases. In other words, when Cp is a variable, or in other words, Cp is some polynomial as a function of temperature, AT cubed plus BT squared plus C times T plus D, something like that. That can be a bear to integrate, can it? Extremely time consuming. So I'm in section 6.5.1 of your textbook, and your textbook plops down an equation 619, that describes a new variable called S0, superscript 0, S0. Okay, so that's a new property, and it's defined in terms of an integral of Cp as a function of T. So that's not Cp times T. It's Cp's as a function of temperature, kind of like a polynomial, divided by T, dt. That's going to be a bear to integrate. That's going to be tough. Integrating from T prime, which is some arbitrary reference temperature, up to our temperature T. And what are we trying to do? We're trying to find delta S from T equals T1 to T equals T2, delta S. All right, so here's what we do. The nice thing here is that this S0 is tabulated in your ideal gas property tables in the back of the book, so that you do not have to do this extremely detailed integral every time you've got an ideal gas with variable specific heat. You say, well, when would I have variable specific heat? That's when the temperature change is large. So for any large temperature change, specific heat is a variable, not a constant. All right, let's look at okay, so if we take this equation 619 and apply it to what we're trying to find, delta S. So here's my integral term, Cp over T dt, right out of the book, minus this term, minus R log P2 over P1, okay? Well, so you can derive this integral from state 1 to state 2 is simply going to be S02 minus S01, and these are going to be lookup values in your property tables in the back of the book. So that's a big reveal. S02, S01, these are not just S's, so please see that with your eyes. S2 minus S1 is not the same as S02 minus S01. Okay, you've got an extra trailing term here that's just pure calculator work, but it's an extra trailing term. All right, let's move ahead. So let's drive towards how do we get S2 minus S1 for an ideal gas with variable specific heat? I've taken, okay, and so I'm reminding you this equation 620 we just showed. So let me come back up here. There it is. So do you see, I was just talking about this on this previous slide. Delta S is S02 minus S01 minus this term here. Okay, so see how this is the same out of your book. So certainly you don't want to depend on these videos alone. You've got to be using your textbook as well. So here's a screenshot of table A22. So this applies to air with variable specific heat, air with where Cp is a variable. So notice here, okay, so let's look at the units for this table. S0 has units kilojoules per kilogram degree K. That's going to be the same as what we're seeking. Yep, okay. Where's our columns? Well, here's our temperature column, and here's our S0 column. And so let's say, for example, T1 was 300 degrees K, and let's say T2 was 520 degrees K. Here's our lookup numbers. We're simply going to go to T equals 300 and write down this number 1.70203 kilojoules per kilogram degree K. And if our temperature is 520, come over here and write down S0 is 2.25997 kilojoules per kilogram degree K. So those are our S0 terms here, but we must remember when we're calculating S2 minus S1, we've got to include in this minus R log P2 over P1 term. Very important. So I've made a type. Don't forget this trailing term, R natural log P2 over P1. Very important. Now, there will be some homework problems that are not air. Now, in my work, during my work experience, nearly all of my ideal gas problems were air. But you will have homework problems that are not air. So for example, if you have a homework problem that's carbon dioxide and you're asked to find the entropy change, S2 minus S1, okay, I've got to go get these S0 terms. I can't use table A22 because that's only for air. I'm going to have to come to table A23, look up carbon dioxide, and the devil's in the details. Look at this table A23. It's got a bar over everything. I've got H bar, U bar, and S0 bar. Well, remember the bar is going to be on a molar basis. So if if you have a homework problem or a test problem and you got to come to table A23, recognize that when you write these S0 bar terms down as a function of temperature, you've got to divide them by the molecular weight of your substance. So if our problem were carbon dioxide, you would take, and let's say your number was 208.717, you would divide that by 32 plus 12, 44. So your S value in kilojoules per kilogram would be 208.7 divided by 44. So that's another little detail that you might put in the back of your mind when you're using table A23. So it's easy to forget. With all these details, it's easy to forget where you're headed. We're looking to find delta S, the change in entropy, little s, from state 1 to state 2. We're told that we need to use variable specific heat. So therefore, we have to find these S0 terms, and we can't forget our R natural log P2 over P1 term. So you see that I've scratched out my old what's the formula text box, right? What's the formula? So I do not want to suggest that you memorize these two formulas, 617 and 618. Now, these are also the ones that we just derived in my own work, but to show you in your textbook, well, gosh, I hate to scratch down stuff off a video slide. You can go to your textbook to equation 617 and 618 and scratch down these quote unquote formulas as you need them. Okay. And in fact, probably the more, okay. And so remember, these were the S0 terms from your textbook. In your textbook for ideal gases with constant specific heat, very common to do this. 6.5.2 also comes out with this very handy relationship, 621 and 622, that we also just derive from the TDS equations. You can write those down, but you definitely want to write down next to these formulas. Applies only to ideal gases with constant specific heat. And remember, if CP is constant, CV is also constant. All right, so I'm straying away a little bit from my what's the formula criticism, but I also don't want to suggest that, oh, you ought to just memorize it. Everybody ought to memorize this. If you're in graduate school, you're going to use this so much that you will have this in your memory bank. At the undergraduate level, not so much. Have you noticed here I've been jabbering on about ideal gases and constant specific heat and variable specific heat and say, man, all this stuff confuses me. It can be confusing if you haven't worked through many engineering problems, and that's probably you. So I've created a video called Decision Trees, trying to help you categorize in your mind what I've got decision trees to go through when I read engineering problems. So for example, what's the substance? And remember, is it a phase change substance? Well, if it's a phase change substance, I go off and do something different. Is it an ideal gas? If we say, oh yeah, I've got an ideal gas here, like air. Well, then it's a decision tree. Then you've got to make another decision. Now am I going to model air as having constant specific heat, CP equals some number, or variable specific heat, CP equals some formula that depends on temperature. And I've got to, if I'm looking for delta S, I've got to go look up an S0 term from table A22. So I hope that helps. So how would you get to my decision tree video? It's 32 minutes. You'd go to my example problems entropy playlist. Go to that playlist, example problems entropy, scroll down, I think to the bottom of the list, and you'll find decision trees. And that might help you in your thinking as you prepare for quizzes and tests so that you can kind of get your thinking gears going instead of totally depending on a formula sheet. Okay, I hope that helps, despite my preaching about formulas and constant specific heat and variable specific heat. Let's recap this important section. we started with the TDS equations, two of them, and our goal was to derive expressions for delta S equals. And we accomplished that. And we accomplished it with these two expressions that apply to any ideal gas, any ideal gas. In other words, an ideal gas with variable specific heat. Okay, so recognize that. So I added a little bit of a formula to this formula, right? Delta S is integral Cp over T dt, complex integral, minus R natural log P2 over P1. And we showed that these S0 terms can be found in the back of the book. Properties, entropy, kilojoules per kilogram degree K. Now, another very powerful problem-solving tool is when you have an ideal gas with constant specific heat. C sub P is some number. CV is some number. And they're related by Cp minus Cv equals R. And then you come up with these two relationships that are really very straightforward. There's just pure old calculator work. Look at this, this bottom one. Delta S is simply C sub P, a number, natural log of T2 over T1, the log of 2, a ratio, minus R, a constant, natural log P2 over P1. So that's just calculator dog work, but straightforward and can be done. Wow, that was kind of a lot to throw at you in one video. I do hope that if you're confused, you might go back and replay some of the videos. But I can assure you that the homework problems that you're going to have in Chapter 6 are you're going to recognize ideal gases. They might be air, might be CO2, might be nitrogen, and you're going to be expected to be able to go through and quantify what is the change in entropy from state 1 to state 2. I hope that helps, and let's continue to work together through Chapter 6 for some more powerful engineering tools.